Hey, welcome back. In this video, we're going to talk about an important mathematical structure in Calc 3 called infinite series. At this point, hopefully, you've been introduced to sequences, infinite sequences, and these ideas of convergence or divergence of infinite sequences. First up, infinite series aren't actually radically new things for you if you've seen sequences and you've dealt with integrals from Calculus 2. In this case, what an infinite series is just a sequence that you're adding the terms together instead of just investigating each term separately. And exactly with sequences, what we have is the definition for AK, so the kth term of a sequence. But importantly for series, what we're doing is adding them together. And we're going to ask the exact same questions as we did with our infinite sequences. Does it converge or diverge? And honestly, that's simply it. An infinite series is an infinite sequence where we're adding the terms together instead of just investigating the separate terms. Importantly, as you'll see, that's where the simplicity ends. One thing before we get going, it's important to note that why these are going to look a lot like integration. Integration is for functions that are continuous. So for any real number, we're given a value. Importantly here for series, we actually have these discrete values. We have a specific value when we have an input of 1 and then 2, but there's no idea of k being 1.5. What you'll see is we're going to have to attack these and the divergence or convergence of these series a bit differently than we did with integration. Up first, we need to talk about partial sums. What we're going to do is define what it means for a series to converge or diverge. But partial sums are simply not going all of the way with the addition of all of these infinite terms, which is really hard to deal with. We actually are going to look at a sequence of partial sums. The partial sums, we're going to use S to denote a sum, and S sub 1 is the first partial sum, and that's simply just the first term, A1, or the first part of this summation. S sub 2 is simply A1 plus A2. You probably can get the idea. We're going to use the verbiage partial sums a lot. If we say the fifth partial sum, that is just adding the first 5 terms of the sequence. And so S of 3 equals A1 plus A2 plus A3. And then I won't go any further than that. We have an idea of what we're doing here. Importantly, though, if we want to write a little formula or a summation for S, the nth partial sum, what we would do is starting at k equals 1, we're just going to go to the nth term of the same description of A sub k. I just want to make a statement for a lot of folks who are first introduced to infinite series. They're pretty complex, or they can seem complex. I think it has a lot to do with notation. You should feel somewhat comfortable with this sigma sum notation. But importantly, listen to what I'm about to say. I can't emphasize this enough. If I'm going to look at the convergence or divergence of a series, what I'm actually going to do is I'm going to look at the convergence or divergence of the sequence of partial sums. So I look at these partial sums at each step, and I create a sequence with those partial sums. So we'll be looking at the infinite sequence of S sub n. And what's beautiful about that is you've seen previously how we deal with the convergence or divergence of infinite sequences, and we take this infinite series and we're going to turn these iterative partial sums into a sequence amongst itself. So the first incredibly important definition is what do we mean when we say a series converges or diverges? And this is it. What we do is we don't add up all those terms in any way. We develop these partial sums, or more importantly, we look to develop a formula for the nth partial sum, and then we look at how that goes to infinity. More specifically, if the sequence of partial sums that we've defined here, we've described S sub 1, S sub 2, S sub 3, yada yada, if that sequence has a limit L, then we say the infinite series converges to that value L. I just want to state that again real fast. In order to find the value and to see the convergence or divergence of the infinite series, what we actually do is look at the convergence or divergence of the sequence developed by the partial sums of that series. So I want to add some important notation to what was just said right there, because this is how I actually attack the problems when I'm asked to evaluate the convergence or divergence of an infinite series. So importantly, if we're trying to evaluate or establish the convergence or divergence of this infinite series, so we have from k equals 1 to infinity of a sub k. What we actually mean by that, by this statement right here, and this is very similar to when we deal with the Riemann sums and integration, what we mean is the limit as n goes to infinity of the summation from k equals 1 to n of the a sub k. But as you can see here, hopefully, this statement right here is exactly the same thing as the nth partial sum. So another way of looking at this is saying we're looking for the limit as n goes to infinity of the nth partial sum. And when we do this s sub n, if we're going to actually do the rigorous work of being able to algebraically to manipulate this and to show this value, we have a formula for this. So this will just be finding the limit of a formula for the nth partial sum. But this value, if its convergence, is L. So again, the value of this limit, and again, we know how to evaluate limits. We have a bunch of different ways of doing that. The value of that limit is equal to the value of that infinite sum and determines its convergence or divergence. And then the statement that I just wrote here follows pretty directly, but just to say it out loud, if we can't find this limit value, or if we find that this infinite sequence of these partial sums diverges, we say that the infinite series diverges. There's a whole lot more to talk about, but before we move forward, I just want to show an example to ground us in this process. Importantly, what you're going to see is dealing with these infinite series can be pretty dang complicated, but sometimes they work out pretty nicely, and that's like this first example right here. So we're looking to see if this infinite series converges or diverges. What I'm going to do out the gates here is I'm just going to play around and list a few of the first partial sums. So first of all here, I have s sub 1. So what this is just the first term. That's when k equals 1. I'm not going to write this all out for board space, but you can pause the video and verify. If k equals 1, what I get is 1 over 1 times 2. So this is 1/2. And then s sub 2, or the second partial sum, would be 1/2 plus what happens when I plug in a 2 into this. So 2 times 3, it'd be 1/6 right there. Let's do a few of these, and then I'll add these up and see if we can see a pattern. So I know it's 1/2 plus 1/6 plus, okay, if I plug in a 3 into this, I get 3 times 4, so 1/12. And one more, so s sub 4, the fourth partial sum. This is kind of easy because when you've done the previous ones, we know that they start exactly the same. We just got to find the next one. Well, this is, by the way, this is 4, so this is 4 times 5. This will be 1/20. You can kind of get an idea here, right? So this term right here, 1/12, was 3 times 4 in the denominator. This is 2 times 3. This is 4 times 5, yada, yada, yada. Importantly, I don't actually care about when I'm investigating these infinite series what each term is. I care about what the summation is, or these partial sums. So I have my first partial sum right here of 1/2. And then for the second partial sum, I have 1/2 plus 1/6. Just again, kind of hand wave it through this. This is 3/6. 3/6 plus 1/6 is 4/6. And that can be reduced down to 2/3. I'll again kind of walk through this third one. I'm going to get lazy with the fourth partial sum. But let's see, this is 2/12. This is 6/12. So 6/12 plus 2/12 is 8/12 plus 1/12 is 9/12. 9/12, which we can reduce with a common factor of 3 to get 3/4. And now I'm going to act like I'm doing mental math and adding these together, yada, 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 reduce, cancel, 4/5. I've actually done this before, but I also know the pattern of these partial sums, and maybe you can see it here. And again, what I want to describe to find whether it's convergent or divergent is can I develop a formula, an explicit formula for the nth partial sum. And what you can see here is that the second partial sum is 2/3. The fourth partial sum is 4/5. And then what we can do is develop a formula. Again, this isn't a rigorous proof, but we're just getting used to these infinite series. Trust me, the nth partial sum for this infinite series ends up being n over n plus 1, right? So the fourth partial sum is 4 over 4 plus 1, which is 5. And again, this step will be hard with most infinite series, but this is set up to work pretty nicely. I've been able to develop a formula for the nth partial sum, and what we need to do is find out does a sequence of these partial sums have a limit? Or in other words, I have this definition right here. So in this case right here, if I'm looking for the value of this infinite series right here, so I have from k equals 1 to infinity of 1 over k times k plus 1, what I've found is that the nth partial sum is defined by this n over n plus 1. Following along to here, what I know is that this infinite series value will be the same as this limit right here, n over n plus 1. That's the formula, the explicit formula for the definition of the nth partial sum. And if we know about our infinite limits right here, we're looking at this. We're looking at the lead terms of the numerator and the denominator. The lead coefficients will give us this value since we have the same degree. This limit goes to 1. Therefore, what this means right here is that this infinite series right here converges to 1. Again, that example is just meant to establish some kind of grounding for what we're doing here. Importantly, you'll see we're not looking at the limit of this definition of each of these terms of infinite series. We have to analyze the partial sums. With the analysis of the partial sums, if we can develop an explicit formula, then we can just apply the limit as n goes to infinity of those terms in that sequence. Let's now look at some rules or properties of these infinite series. So here we have just 3 properties of infinite series that are very useful when trying to evaluate the value of an infinite series or determine if it converges or diverges. In this case right here, importantly, we're saying that these 2 infinite series, we know they're convergent. So if that's true, then if we have terms of our infinite series described by AK plus BK, again, exactly these same definitions right here, we have the ability to split up this summation. Importantly, these 3 properties are the same as integrals because we have limits being applied to infinite sums. So these 3 properties are properties of limits and of infinite sums. Therefore, they become properties of these infinite series. So here, the value of this more complex infinite series is the same as the series from 1 to infinity of a sub k, and then adding the infinite series from k equals 1 to infinity of bk. So this would be the sum property of infinite series. We have now the difference property, means exactly the same thing. If we have multiple terms but they're being subtracted, we can evaluate those separately. And you'll see in a lot of cases where this is really useful. It takes a more complex series, infinite series, and splits it up into easy series that are easy to attack. So we're going to just subtract the infinite series of the BKs. And finally, we have what we've always called the constant multiple rule. If we have a constant, so it's some constant in each of these terms times the definition of these k terms, what we can simply do is pull out that constant and evaluate the infinite series without that constant. So we've now established the definition of an infinite series, the convergence or divergence of an infinite series, seen an example, and established some basic properties.